Hi, I'm Elaina Landrum, and this is my presentation on Lab 5, which is a study of Faraday's law. There are a few key concepts necessary for completing this lab. The first is Faraday's law and how a magnetic field interacts with a conductor to induce a current, and how this current in turn produces an electromotive force and a Curly electric field. In this lab, we focused on a magnetic field that changed with time. The Biot-Savart law was an important concept in this lab as well because we had to model the conducting tube as a collection of rings, and we used the Biot-Savart law to calculate the force on each ring by the falling magnet. Newton's second and third laws played a role in the procedure too. We had to implement Newton's second law in the code in order to update the position and velocity of the falling magnet, and we used Newton's third law to find the equal and opposite force on the magnet by the tube. My final results are shown for the average experimental time versus the calculated time the magnet spends in the tube. Before actually doing the experiment, I recorded the measurements of the aluminum foil tube and the magnet. The length and thickness of the tube are listed, as well as the mass and mu, the magnitude of the magnetic dipole moment of the magnet. This mu value is taken from my results in Lab 3. For the procedure of this lab, I had to drop the magnet through the aluminum tube and record how much time had elapsed between when it entered the top and exited the bottom of the tube. Then I repeated the trial 4 more times and found the average time. My time trials are shown in the middle of this slide, and the average time I found was 1.982 seconds. To the right of this slide, I included a visualization of how the code splits up the aluminum foil tube. The model visualizes the tube as a collection of individual rings that the magnet is falling through. In order to create this model, I had to write one function to find the magnetic field at a point and another to find the change in magnetic flux over the area of each ring. Then I used a simulation loop to model the magnet falling through the tube. From the change in flux, I calculated the induced current in each ring and colored the ring red or blue based on whether the current was flowing clockwise or counterclockwise. Then I calculated both the gravitational and magnetic force acting on the magnet and summed them to get the net force on the magnet. From here, I updated the velocity and position of the magnet so the computational model could accurately show how the magnet moves through the tube. Finally, I plotted the velocity versus time to see how the net force on the magnet affected its movement. On this slide, I've included some pictures of my code. On the top left is my function for finding the magnetic field at a point. I derived this from Coulomb's law. On the bottom left is my function for finding the change in flux over time. This is from an equation in video lecture 43 that details how to calculate the change in flux from the radius, distance, speed, and magnetic dipole moment. On the right is a picture of the velocity versus time graph that my code produced. For a majority of the graph, the velocity is constant, which means there is no acceleration. The magnet falls more slowly through this tube than if it were just falling through the air. Now we have some of the coding related questions. The way the coloring of the tube worked is as the magnet moved down, the rings directly below the magnet were colored red and the rings directly above were colored blue. The red corresponded to a clockwise induced current and the blue corresponded to a counterclockwise induced current when viewed from the top. We can determine this by pointing our right thumb in the opposite direction of the change in flux, and whichever way our fingers curl is the direction of the induced current. If we drop the magnet into the tube flipped the other way, the results of the experiment shouldn't change, but the induced current in the rings of the tube will be in the opposite direction. In terms of how my recorded time compared with the computed time, my recorded time was longer. This could be due to error in the computation of my mu value from Lab 3. My recorded time also seemed shorter than it should have been, which I think is because my aluminum was relatively thin. Finally, the velocity on the graph is mostly flat, meaning there is no acceleration, and so the net force acting on the magnet in the tube is 0. For the conceptual questions, if the resistivity of the conductor was closer to 0, this would increase the induced current, which would then increase the magnetic force acting on the magnet. This would make the magnet fall more slowly through the tube. If there were holes cut into the aluminum tube, then the horizontal slices of the tube at those spots would no longer be full rings, so the current couldn't flow anymore. Less current means a smaller magnetic force would be acting on the magnet, so the magnet will fall more quickly through the tube. I've restated my final results here on my conclusion slide, where my recorded elapsed time was 1.982 seconds and my computed time was 1.259 seconds. Overall, this lab really helped me better understand Faraday's law and how so many variations affect so many other things in the system. I've restated my final results here on my conclusion slide, where my recorded elapsed time was 1.982 seconds and my computed time was 1.259 seconds. Overall, this lab really helped me better understand Faraday's law and how so many variations affect so many other things in the system.